Part 1, I am going to present about steam nozzle. First one, the convergent type nozzle. The left hand side, first cross section represented as inlet, and the second cross section represented outlet. The types of steams will provide in the different character like entropy, enthalpy, and specific volume. If P2 is not given, P2 divided by P1 is equal to 2 divided by n plus 1 power n by n minus 1. Here, according to the steam condition, the n value will differ. N is equal to 1.035 plus 0.1 x for wet steam. N is equal to 1.135 for saturated steam. N is equal to 1.3 for superheated steam. S1 is equal to S2 isentropic expansion process. The dry set, first one, wet steam. Here pressure or temperature and dryness fraction will be accumulated with that steam quality like X. The dry saturated steam, inlet pressure or temperature. Let's say S is equal to Sg, kilojoule by kilogram Kelvin. H is equal to Hg, kilojoule by kilogram. Specific volume is equal to Vg, meter cube per kilogram. Superheated steam also will provide in that same condition, but we have used the steam table 3, 4 and 5 for calculating or for selecting the specific volume, enthalpy, entropy respectively. And the entropy of superheated steam can be calculated from Sg plus Cp ln T super divided by T saturated. H is equal to Hg plus Cp into T super minus T saturated. Formula for all three types of steam: exit velocity if inlet velocity neglected, C2 is equal to 44.72 square root of H1 minus H2. Exit velocity if inlet velocity considered, C2 is equal to C1 square root of C1 square plus 2000 multiply with H1 minus H2. This unit will be meter per second. Then mass flow rate also A2 and multiply with velocity divided by x2 multiply with specific volume of the steam, and total mass flow rate multiply with power developed. Number of nozzle n is equal to total mass flow rate divided by mass flow rate per nozzle. Exit area we can calculate from m2 multiply with x2 v2 divided by c2. Area ratio a2 divided by a1 is equal to x2 v2 divided by c2 multiply with c1 divided by x1 v1. Nozzle efficiency eta is equal to 1 minus loss due to friction. Overall efficiency of nozzle is equal to actual heat drop divided by isentropic heat drop. He is equal to H1 minus H2 dash divided by H1 minus H2. Neglect nozzle efficiency if not given. And then convergent, divergent nozzle, inlet and the outlet, in between we have a throat. So if P2 is not given, we can use the P2 divided by P1 is equal to T2 divided by n plus 1 power n by n minus 1 formula to obtain the P2 value. And remaining values will be same, already known value. And the formula for all three types of steam, the section 1 to 2, exit velocity can calculate from 47.72 square root of H1 minus H2. Exit velocity if inlet velocity considered, C2 is equal to square root of C1 square plus 2000 multiplied with H1 minus H2. And the exit velocity of section 1 to 3, the C3 is equal to square root of C1 square plus 2000 H1 minus H3. And exit velocity, if inlet velocity neglected, the C3 is equal to 44.72 multiplied with square root of H1 minus H3. Mass flow rate out exit is equal to A2 C2 divided by X2 V2, and total mass flow rate multiplied with power developed, and number of nozzle total number mass flow rate divided by mass flow rate per nozzle. The area exit area is equal to M2 multiplied with X2 V2 divided by C2. Area ratio A2 divided by A1 is equal to X2 V2 divided by C2. Nozzle efficiency eta is equal to 1 minus loss due to friction. Overall efficiency actual heat drop divided by isentropic heat drop. Note, the neglect nozzle efficiency is not given. The superheated supersaturated steam exit velocity for convergent nozzle. Here the P1 is equal to inlet pressure Newton per meter square, V1 is equal to inlet specific volume meter cube per square, P2 is equal to exit pressure Newton per meter square, where we can calculate the exit specific volume V2 is equal to V1 multiplied with P2 by P1 power 1 by n. Mass flow rate at the exit is equal to A2 C2 divided by V2 kilogram per second. And also we can derive the problem from the data which is expressed for condition of maximum mass flow rate and velocity. The fluid flow through a nozzle is a function of PV power n is equal to C. Here n is equal to 1.135 for saturated stream or dry stream, and n is equal to 1.3 means the condition of steam will be superheated. N is equal to 1.035 plus 0.1 alpha for wet steam. In a nozzle where pressure reduces, entropy reduces. According to this process, polytropic process, and then the reduction in enthalpy is equal to H1 minus H2 is equal to minus integral of V dP, and then we can calculate the maximum discharge after calculating the velocity of C2. In the maximum discharge will be A2 C2 divided by V2. After that we can calculate the condition for maximum mass flow rate, and then we can calculate the dry saturated stream n is equal to 1.135. From that we can calculate that P2 value, and then superheated steam n is equal to 1.3. After that we can calculate the pressure value, and then mass velocity, that maximum mass flow rate will be calculated. Finally we can calculate the maximum velocity through the C2 formula. This maximum mass flow rate depends only on initial steam condition and throat area. It is independent of finite pressure of steam. The addition of divergent part after throat does not affect discharge of steam. It accurate the steam during the nozzle. Thanks for watching this video. This continuation will be the next video.